Woohoo! Welcome back! Today we're going to talk about 9.6, properties of logarithms. Woohoo! I know, everybody's favorite section. But this is actually kind of cool. The algebra behind it is kind of interesting. But there are a lot of little details. So I've tried to break it up in a slightly different way than the book has done to try to express the different intricacies of working with logarithms. Now, the big world of logarithms is amazingly large, and we're not going to really go into all of it. So definitely read the book if you'd like more information. And as always, ask me questions. I've got Sharktopus here as my support carnivore. He's having some trouble with the tentacle today. It happens. Everyone has a bad tentacle day. So let's go ahead and get started. Logarithms and exponential functions are ding, 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 inverses. They were actually set up that way. That was the way they were set up. Remember that logarithms came about as a way to work with exponential functions, exponential expressions. And so we've got this really amazing thing. I'm going to ask Sharktopus to move a little bit. Pardon me, Sharktopus. There you go. Here he is, just hanging out. So log base a of a to the x is just x. That's the log of the exponential expression. So the log of the exponential goes back to the x. This, of course, is silly. This isn't really math over here. This is more of a meta sort of thing. This happens whenever a is greater than 0. Remember, we don't have logarithms we don't have log base 0, for example. We don't have log base 1. Both of those would be either, useless or hard to work with, depending on your perspective. And we don't have negative bases, just because that would be really, really hard to work with. And as long as these bases match, log base a of a to the x, it resolves to just x. It simplifies. It's really lovely. And it works the other way. If you take base a and raise it to the power of a logarithm, you take the exponential and then the exponent in the exponential expression is the logarithm, we also return to x. So a raised to the log base a of x is x. Woohoo! And it's possible, depending on what time of day you're watching this, all of that just sounded like blah, 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 blah. So in order to show you what I really mean, I figured, hey, why don't we come up with some examples? So log base 3 of 3 to the 4th. So again, log base 3 of 3 to the 4th. And you see here for Sharktopus, I'll go ahead and use blue. You see how the base of the log and the base of the exponential match? These are matching. They have to match. If the base of the logarithm and the base of this exponential 3 to the 4th match, log base 3 of 3 to the 4th is, you got it, 4. So the whole thing simplifies. Like, it's really lovely, isn't it? Okay. Oh no, number 2 had to go and be all hard. Well, the thing is first off, this is written kind of in slang. Remember, if we have a logarithm and we don't have a base written in, and it's written out as log, then it's log base 10. It's the common log, right? So I've got log base 10 of 1,000. Now, we've done problems like this already, but I want to try to use this rule. So let's take a look at this. I want to come up with a matching base and a matching base for the exponential. So I want log base 10 of 10 to some exponent. Log base 10 of 10 to the, and then we think, this is 10 to what power? 1,000 is 10 to the 3rd. Woohoo! Yay! And yet again, we have a matching base for the logarithm, base for the exponential expression. They match. Life is good. Log base 10 of 10 cubed. 1,000 is 10 cubed. We get 3. Yay! And I'm going to put them in boxes because it's so amazing. Isn't that lovely? Log of 1,000 is just 3. Easy peasy. No, I lie. It's not easy peasy at all. This is not obvious stuff. That's why I'm going over it. Hopefully now you're looking at it going, oh, I get it. But let's try some harder ones. Oh, no. I had to ruin everything and bring in decimals. Ugh. But we can totally do this. First thing we want to do is translate the slang. This is a log means common log. So we do log base 10 of 0.01. Now, to follow this pattern, we've got a base of 10. So we need to figure out what this is. And this is 0.01 is 1 over 100 or 1/100th, depending on your perspective. That's 1 over 10 squared, which is 10 to the negative 2. Ooh, that decimal 1/100th is just 10 to the negative 2. Now, it's fine if you knew that right off the bat, if you go directly there. I just wanted to kind of jog everyone's memories if you were feeling a little rusty. So what we've really got is, oh my goodness, I took up too much space. Log base 10 of 10 to the negative 2, right? Because we plug that guy in right there. The bases match, and we get, right off screen, negative 2. Ooh, let me scooch this over. There we go. There's negative 2. So basically, if I'm saying log, remember, log means log base 10, and then I'm saying, what is this in terms of 10? Base 10. 10 to the what power gives me, in this case, 1/100th? And the answer is the power is negative 2. Okay, we're going to switch gears, and now we're going to go into exponential first. So I've got e raised to the natural log of 4. So again, I always rewrite it, make sure I understand it. Natural log, also kind of slang, right? This is a well, technically it's a symbol, but it's 2 letters that represent another log. It's log base e of 4. Now in this case, I'll use a slightly different color. If this matches this, because we're doing the exponential first, see how those 2 bases match? If they match, everything disappears and we end up with just the 4. Right, like that. It's not necessary to be able to trill your R's to do math, but it does come in handy. Okay, shall we do one more problem? Woohoo! Again, 10 raised to the power log, and this is common log of 5. There's no base. 10 raised to the log of 5. That's 10 raised to the log base 10 of 5. I've got my matching bases. Woohoo! And that means, you got it, get your trill ready. We end up with 5. Woohoo! And I should probably put squares around these, or rectangles really, or parallelograms, or quadrangles, something. Anyone up for a rhombus? So we've got, woohoo, the first page done. So this is logarithms and exponential functions are inverses. In other words, they undo each other. So if you take the logarithm of an exponential and the bases match, everything cancels. If you raise a base up to a logarithm with the same base, again, they undo each other and you end up with the 4. Isn't that lovely? Oh, so good. Okay, let's go on. Let's look what the next one we have to look at is. Dun dun dun! Oh, it's not too bad at all. We're totally gonna survive this. Okay, so next up, expanding logarithms of products and quotients. Because of the relationship between logs and exponents or exponentials, we get the following properties. Now, these are very, very particular, and they're very easy to forget. And I have to warn you that these are These properties are things that don't come up a lot. They come up very rarely, but then suddenly in math, you'll be taking a math class and suddenly the teacher will say, remember logarithms? And everyone gasps. So what I would definitely recommend is if you're going to go on in math, by which I mean if you know you're going on to say calculus, I would encourage you to hold on to these logarithm notes, take pictures of them, store them somewhere away where you can get to them, because logarithms will come back up again. And you will, at that moment, you'll be like, oh no, I can't remember how to do this. So hold on to these notes. Okay, let's talk about it. The logarithm has to be taken of a product. So the product of a times b. Not a plus b, but a times b. If we do that, we get log of a plus log of b, which makes sense because remember, logarithm is saying what's the exponential, what's the exponent. It's looking for that. And if we're talking about exponents, if we multiply two things together, you're actually adding their exponents. And the same thing with division. If you take the logarithm of a divided by b, then you get log a minus log b. Now, why in the world are we doing this? Well, it turns out that sometimes we're going to have to take a big, nasty logarithm of a big, nasty expression, and we're going to need to break it down into things we could either work on with our calculator or that we could work on in other ways. And here, spoilers, calculus. So we're going to need to break down big expressions into smaller pieces. The good news is, though, that for us, we're going to stop here. We're just going to break them down. We're not going to go to the next step. The bad news is that because of this, you won't see why we're going to do this very much. You're just going to see us do it, and then you're going to say, why did we even do that? And I'm just going to have to say, because, with a big wink, and I might say something about calculus or engineering or, further studies. And then it will be a big surprise and you'll be thrilled. Okay, so simplify or expand these logarithms. So I've come up with a few logarithms that we can look at, and I can show you what we can do with them. So I've got log base 2 of 14. Now in this case, normally log base 2, what we've been hoping for is that whatever's in here, that this would be a power of 2. 14 is not a power of 2. 14 is 2 times 7. So what we're going to have to do is take a look at other ways to break this down. 14 is 2 times 7. Ooh, that's exciting. If 14 is 2 times 7, then what I can do is I can break this down into log base 2 of 2 plus log base 2 of 7. Now, if I were a student, I would say, yay, we've taken a single logarithm and now we have 2 logarithms. How is that better? And the answer is, well, this one, log base 2 of 2 equals 1. And so really what we're doing, and this is probably most closely related to when we were working with radicals at square roots, and we were trying to squeeze everything out of that cabin, get everyone out of the cabin. We're doing the same thing. The goal is to get squeeze that toothpaste out of the tube, squeeze as much as you can out of the logarithm so we can get non-logarithmic numbers or other expressions that are going to be easier to work with, and leave as little as possible inside the logarithm, or, with the bunny fur, as it were. So, believe it or not, this is considered a more simplified form, I guess, or an expanded form if you prefer. It depends on your perspective. This is considered less simplified, less expanded, so we would always try to go for this one. I know, I know. A lot of people are just shaking their head saying, I don't see why this is happening. And again, unfortunately, you're not going to be able to see a lot of it, but you just take my word for it. This is very helpful later on. It'll be a little bit helpful in this class because we'll give you a couple problems about it, but really it comes up later on. Okay, so again, a lot of times with when you're expanding logarithms, you just go with the most obvious expansion and see if it makes sense. I see a 10 times the y inside. So I've got this where I've got a times b. I'm going to expand the logarithm to each of them. So logarithm, or log of 10 times y, is equal to log of 10 plus log of y. So far, so good. And then I remember, and you may remember, but just in case you don't, log base 10 of 10 plus log, I don't need to make this fancy. I can just log of y, although for me this looks like loggy. And if that's a concern for you that you just see it as loggy, or even worse, eogy, you may want to keep the parentheses in. Notice I put a little bit of gap there so it doesn't just turn into a single word in English. So again, parentheses are optional. You may prefer the way it looks, but log base 10 of 10 is 1, yay! So 1 plus log of y, or 1 plus log of y, if you prefer. Oh, let me scooch that over again. Woohoo! Okay, shall we try another one? Yay! This is so exciting. This has been so satisfying. Yay, everything's going so well. What could possibly go wrong? Dun, dun, dun! Okay, well, 3 times y, there's only one way to break it up, so I've got log of 3 times y. Okay, I lied. There are lots of ways to break it up. There's only one obvious way to break it up, right? 3 times y. If you wanted to, you could break it up as, 2 times 1.5 y or something like that. Okay, log of 3 plus log of y. And neither of those simplifies. So we just leave it like that. That's it. So notice the instructions: simplify or expand these logarithms. And I should say and or up there. So we are, because in English I should say and or. In math you can just say or and it works. Log of 3, no simplification there. Log of y, we don't know what y is, so maybe it simplifies depending on what your y is, but we don't know it, so we can't possibly do it. And so that's it. And of course you could write it log of 3 plus log, and be very careful, give it some spacing. And that's our final answer for that one. Woohoo! I know you're very, very excited. But I don't want, I don't want to give you too much exciting stuff. So I'm going to give you guys a chance to calm down and take a deep breath and go get some fresh air, maybe some exercise, vegetables, hydrate, hydrate, hydrate. Go spend a little time thinking about how awesome you are and how amazing your brain is, and come back and we'll do some more. Okay? Super fun. I know everyone's like, yay, more logarithms. Just what I wanted. And it's like, I know, I'm there for you. I've got the things you want to know. Woohoo. So, math on and woohoo, and I'll see you in the very next video. Yay!